Okay, one thing I needed to let you know, the final project has been preliminarily announced in the core website. So you had better check that because presentation day probably just one month from today. So you need to basically you need to find the topics. So probably at the end of this course, I will ask you present your topic, your final topic. So to let everybody know what kind of project you are working on. But so make sure you do download the instruction of the final project and go through with the instruction and the regulation there. Basically, I'm not going to expect that you repeat the work that has been done in the by the previous students who took this course. Okay, so I kind of list the work, the final work of the previous students and put their works on the website. So you need to check what kind of final project has been conducted by those students. So your topic will not be overlapped with that which has been presented. So you need to find a project something for your final work. So, and I think in the instruction I have declared the topic clearly, so you can. Anyway, if you have any question, probably we will discuss that in the next month. But before that, you need to go through the restriction and the instruction of that final project. Okay, so before final project, we still have two assignments, which one of them will be instructed in today's lab time. So I think we expect that we should have a final assignment probably in the next week. So next week the final project should be a multi-layer construction. It's a neural network project. So that will be all for this semester's lab assignment. Okay. Other than that, that should be the final project. So you need to start your searching your final project topic as soon as possible. Okay, and I have graded the assignment 7. I think it's just half of you implement the genetic GA correctly. So half of you are not really implement the correct one. So I will use a sample to refresh you what kind of operation should be done in genetic GA. So I'm asking you that you go back to your assignment 7 and correct your genetic GA to make sure the operation of your genetic GA work correctly. And then resubmit the corrected genetic GA to solve assignment 8. So what I'm saying is that you need to resubmit assignment 8. I think the deadline I will set it to the end of this week. So make sure you resubmit assignment 8 with the corrected genetic GA solver. Okay? All right. So assignment 8, I will grade the score after the weekend. So you need to resubmit your assignment 8. But before that, you go back to your genetic GA solver to see if you have similar problem. And most of you, if you take a look at the comment that I added in your score, you might know what is the problem with your genetic GA. And if you are not understand what I mean, what I said in the comment, I will use one example of your work and try to let us refresh what kind of procedure should be done in our genetic GA solver. So in order to make your GA solver compute or evolve the best solution correct. Okay. So before we start, is there any particular question about your assignment or the topic you the slide right now. I think right now you should step into the neural network, right? So is there any question about the slide, about the video content, or the assignment you are working on, or a previous assignment you have done? Is there any particular problem you'd like to ask now? Okay, if you don't have a problem, I might spend probably 1 hour for to refresh what should be done correctly in your generic GS solver. Okay, so I kind of use students' work, try to correct, try to make your GS solver correct. Okay, let me check. Did I start it? Yes.
老师，你这是麦克风有开吗？
应该是有哈，我确认一下。
确认一下吧。
有了 ，audio 这边有在闪啊，好吧。Okay, I will use Rachel's project and to let us go through what implementation has been done there and what's wrong with the implementation. Okay, so before that, I'd like to ask you go back to the instruction, assignment 7. C#. So take a look at this data structure we designed. We kind of designed it. I mean, for our generic operation. So as you can see, I mean, interface-wise, what a GA interact with the user probably just 3 buttons, right? And the property grid, sure, for sure for that to let the user modify the parameter for the GA. But the so interface function, the most important function should be reset because the user might change certain kind of specification. For example, the mutation rate or population size, such kind of thing. So we need to reallocate memory. I mean, for the GS solver. And after that, I use my quick run one iteration. So the most important procedure should be done in the run one iteration. And the run to end is just a looping. Just a looping for executing the run one iteration, right? So if you go back to the your generic GS solver, so make sure you did not involve any problem-dependent data in your generic GS solver. And I think some of you have added that penalty to your GS, and definitely that is not correct one. You need to think that what you are developing is a generic GS solver. A general GS solver. So a general GS should know nothing about the problem. In this way, your GA can be applied, can be reused repeatedly to solve different kind of automation problem. Okay, so I think this Rachel have added a penalty factor right here. It is not GS data, right? It is the problem-dependent data. So you need to move that out. Okay, I don't know which one initiated this wrong idea. Okay, so comment that out, don't put it in here. So definitely there should be no any penalty stuck there. You need to think about that. What if GA is solving a problem without any penalty? Then you ask that guy, surprise the penalty value is really it's very peculiar, right? So the user might not get it. So penalty definitely is not a data for the GS solver. It is your problem. That should be done in your problem class or your main phone class. So we comment that out first, right? And if you still have problem, we can compile it. All right, so everything is working, even though you don't. And it's that related, and also, well, if you look into the generic GS solver, we kind of define enumeration, right? Mutation, mode, automation type, selection type, and also the classes right here. So as I just mentioned, the most important interfacing function should be what? Should be reset and run one iteration, right? So if you are a guy which is very serious about the memory allocation, in fact, in your reset, you can add a certain kind of condition, not blindly reallocate memory each time when user click on the reset button. So if I want to improve the efficiency, what I can do in reset is that if, well, as you can see, all this data we designed it for GA evolution, they always involve an array, right? So array, the size of array depends on the most important data should be the population size, right? Okay, so maybe we can stick on indexes because these array are related together. They are dependent on the size of the population size. So we can check one if indices equal none in the very beginning, right? In the very beginning, indices array there is no any memory allocated. So if this situation happens, then definitely we need to reallocate memory for every array, right? Or what? Or indices length. If it is not known, definitely it has been memory has been allocated previous, right? If length does not equal current value, current population size times 3. If this situation happen, only in this situation I need to reallocate memory. That is much better. I mean, you seriously concern about the memory allocation, right? If index is none, definitely it is in the very beginning condition. So we need to allocate memory for that. Otherwise, probably user did not change the population size, right? And the initial setting is okay. We are not going to reallocate memory for blindly reallocate memory because the population size is still the same, right? And comparing with the previous case, right? So only in this case we need to reallocate memory. So that means you are a serious guys about the memory allocation. You don't do amazing blindly memory allocation there. Okay, so reset. What we need to do is that so number of gene. It's okay. So we also need to include this guy, right? Because there is also population dependent. So I kind of move this part within this process. So that means if memory or array has not been allocated, I need to allocate it. Or population size is different from the previous time, then I need to reallocate it. So after initialization, we set everything there. So we set it. Okay, so it's okay. That is much better. I mean, we are not going to blindly allocate memory each time. Okay, so that's reset. And if you look into the data memory, is that because all these data are population size dependent, so we need to reallocate memory for them. Okay, so let us take a look at the GA operation. So that should be the run one iteration here. Run one iteration. So run one iteration, we kind of print this kind of function, right? Perform crossover operation, perform mutation operation, perform selection operation, and that is not correct. Update so far the basic solution objectivity. This function should be done in front of the selection operation, because after selection operation, the population has been changed. So we need to update the so far the best before the population is changed. All right. So normally, what I'm expecting that you need to update so far the best solution before the selection operation, because after the selection operation, the population has been overridden by best or fitter children or parent, right? So we need to calculate the iteration best, calculate the iteration average right here in this function before we do the selection. Okay, so that's the idea. So what we have done is right here. So actually, it's during the initialization, initially we set up this randomly initialize the gene right here, and also we evaluate the objective value right here. So in the very beginning, right? So after that, we enter the round one iteration. So round one iteration, first we use this array, just shuffle these parts. So probably of the shuffle, maybe the list should be 9, 7, 6, 1, 4, 0. Does not matter. So pair-wise, we assign the parent ID for crossover. So we use this. This is the first time we use the indices to help us pairing a pair or parent for crossover a pair of children. Right. So that is the first time we use it. So that has been done in the perform crossover operation. So after that, we conduct the perform mutation operation. But remember that once we finish the initialization, we compute the objective, and then in the perform crossover operation, we also that the derived class generate mutated children right here, and also in the genetic solver, we compute the objective value right here. So it's done right here. So similarly, for the mutation operation, we let the derived class mutate the genes, and then we compute this point. So once we finish the mutation crossover operation, this data has been updated right here. And does not matter, probably fitness value, fitness array, they contain the previous data. We don't care about that. So after that, we need to find the best iteration best. So we need to go through from the parent up to the mutated children. We need to go through the objective value, right? We need to go to objective value, and then find the ID first. So suppose the ID is right here. This guy is the iteration best, and also we need to calculate the iteration average, right? So you should do the coding, but you also don't use the array, because right now, as you can see, the objective array right here is we did not use up all the element there. So some of you use array because let me show you. Okay, so let me go to update so far the best solution. So update so far the best solution, we need to look through objective array for parent and children crossover chromosome, right? So we look through it, but we need to find the best one. So we need to check the minimization, whether it is minimization or maximization, right? But we also have defined a function, right? Convert the compute fitness. Okay. Set fitness from objective value, right? So it's a function because I kind of set it as a function because to let you concentrate on the task of converting an objective value into the fitness, right? So within this function, we also need to identify whether the problem is maximization or minimization, right? So similarly, right? So that function that basically is that we convert each objective value into its fitness, right? So it's really straightforward. But again, as you can see, the array of fitness, we did not use up all the element here. If you like to find the iteration average, some of you wrongly use so-called extended function on an array to get this average value, which is not correct. Okay, So what I'm saying is that some of you should update. Okay, right here. So in update so far the better solution, we need to compute the iteration best and iteration best. That's right. So some of you use this this kind of so-called OBJ objective is an array, right? So array, if you list out the variable function on array, as you can see, this is a normal. Well, this symbol stands for the normal operation or normal function for array, and these figures meaning that is the extended method. So extended method, if you click on this, there are a bunch of extended method max, right? So you get a maximum value, objective value. You will get a minimum value, objective value. It's an array. Get average. Wow, it's beautiful, right? It can compute the average for us, right? But definitely it involves computation resources in order to compute the maxima, right? So behind this function, actually, the computer loops through each item once to get the maximum value returned to you. And then this function execute another iteration through all your items again. So we call this one-pass algorithm, two-pass algorithm, three-pass algorithm. So you spend a lot of CPU time to traverse all your elements one time, second time, third time, which is really inefficient. What you need to do is that you set up just one-pass algorithm. You simply build up a for loop. I start from 0 and I up to the limit or the total. That is the correct one. You should do it. So you should always try to implement your own for loop to traverse your array just one time to get all these values in one pass algorithm. So pay attention to this kind of stuff. So don't be attractive to use this kind of so-called extension function. It's costly, all right? Make sure you understand that it's costly and probably wrongly, right? Because as you can see, the length objective up to this point. So all these elements probably contain some previous value, and then if you directly call this function average, you will get wrong average for this iteration. So don't be attempted to use this kind of so-called extended function. It's costly, and it might compute the wrong answer for you. Okay, so make sure you understand that. All right, so in update so far the better solution, right? So we need to calculate the iteration base. So what you need to do, exactly what you need to do is that you loop through the objective value, right? So you identify which one is the best. So suppose this is the iteration best. And then you don't need to, within this loop, you don't need to check the objective value with the so far the best value right here. You don't need to do that. Once you simply loop through your chromosome array one pass, and then identify which one is the best one. And after this looping, you check the value, check the objective value, whether this objective value is better than so far the best objective value. So suppose the ID is right here, and then you check the objective value. If the objective value is better, then so the better. So what you need to do is that gene-wise copy each gene to this place. Don't just copy the array reference. It's wrong. I mean, I see probably one or two guys make the wrong setting. You need to do, as I say once again, you need to gene-wise copy each gene value to here. If you simply just copy the reference, there is a reference referring to this array, and then you are so far the best solution is here. If the address right now is 77, it's the best one, right? So 77 is right. You copy 77, and then it is no longer pointed to this array. It will be changed to this place. That is called shallow copy. It's wrong. You need to gene-wisely copy every element to this array. Okay, so some of you guys still make another mistake. All right, so if you don't understand the intrinsic structure, you just talk to me. I will show you what's wrong there. Okay, so you need to do the gene-wise copy there. Okay, so probably you guys might think, well, why should I do the fitness value calculation in one pass, right? So in one, because we need the fitness value. We need the fitness value in order to do the selection. So in the selection operation, we will do the selection, use this array and the fitness array to do it, either it's a deterministic selection or stochastic selection. So these two data will be reused in the selection operation. But probably we may set some computation effect, some computation right here. So in update so far the best solution objective, probably we will do in that case I mean a better way is that we so we might simply because this is set fitness from objective, right? So actually within this function we loop through our chromosome one times total, right? But as you can see, during this operation, update so far the best solution and objectivity, we again loop through the population once again. So actually, in this function, you can combine update so far the best solution. You can combine the operation right here, right? Or simply call it once. Call this function once. So that means if you perform this operation in two steps, what you need to do is that you call fitness before you do the updates so far the best solution. You kind of compute the fitness value first. So once we get the fitness value right here, we don't need to directly check the objective value. So in order to find the best ID, what you need to do is just go through the fitness value, the largest one. No matter it is optimization, it is minimization or maximization problem. What we need to, if you compute the fitness value, I mean in front of the before you loop through the chromosome in order to get the iteration average and the iteration best, you can just directly check the fitness value. You don't need to use this kind of coding right here. So what I'm saying is that you can improve the computation efficiencies here. So I'm saying is that update so far the best solution and objective. What you need to do probably just call set fitness value. So you set up the fitness array first, and then you don't need to bother about minimization or maximization anyway. So what you need to do probably just forget about this checking. And forget about these cases because most of the code should be similar, right? So we can save that, right? Because we have the fitness value available. So we look through, well, actually this is not really the best one because still we look through the chromosome one time, one pass. Another pass, we will compute the average. So far the best, okay, so it's wrong right here. It is not right, right? So this part is not correct. So start from total, right? So what we need to do is that iteration, we need to compute the iteration average. Iteration average objective is set it to 0, iteration ID, probably iteration, oh no. Oh, okay, never mind. I set up the best ID, maybe -1. So iteration average is start from 0, and then, so we loop through our, it's not wrong. It's not right. I mean, you keep checking the current objectivity, whether it is better than the so the best or no. It's not right. What we need to do is that we get average, iteration average, and iteration best ID. That's it. So within this one pass, we simply identify for that. So we initialize the average, right, 0. So we kind of add it up. We will compute the sum first, right? So objective value. The ith chromosome. So we add it up. And then, because we have fitness value already there, right? So we call this function in front of this looping, so we can check if fitness value for this guy the largest one should be the better one, right? So we needed to set up a local variable double the largest fit, maybe perfect double start from minimum value, right? So if the fitness is greater than the largest fit, then what? We update the largest fit. Directly use the fitness value. And then I need to find the best ID. Should be the I, right? So the purpose for this looping, we need to identify which one is the best. So we will identify the best ID. That's it. But we will take advantage of the computed fitness value because computed fitness measure should be the largest one, should always be the better one. So we don't need to separate our algorithm into these two parts, minimization. We don't care whether it is minimization or maximization because the fitness measure has compute that from the objective value. So what we need to do is that. So we find the iteration value. So after this looping, right? So after this loop, just one loop. So we conduct another pass, right? So after that, we will compute what? Iteration average. So iteration average, right? Again, don't use sum, all right? Don't use sum, don't use maximum, don't use minimum, don't use average because you can write your code just one pass only up to total, not to the end of this array. Okay. So after that, you can just use divide concatenator operator. Divide it by the not the dense, right? Not the dense, should be the total. That's it. So we get an iteration average. And then, since you know the iteration base, right? Iteration base ID, you know iteration base ID. So this time you need to check whether it is maximization or not. If iteration base objective, no, not the maximum value. So, well, okay, so you need to iteration. So iteration best objective. It's obvious. So objective variable. Which one? Iteration best ID. The best ID. Excuse me. The best ID, right? So you get the iteration best objective. Does not matter whether it is minimization or maximization problem, right? But we need to check iteration best is better than so far the best. So this time we need to check the condition automation. So if it is maximization, and if iteration based objective, right? Because we have computed that objective is larger than so far the best objective, right? So this condition, if this condition happen, then we should update the so far the best, right? So it will be complicated, right? So we can combine this condition again. If optimization condition is maximization and iteration best is larger than so far the best version. So that is the condition, right? Another condition is another condition is that if it is maximized, if the condition, so we kind of use or. It is a minimization problem, and the iteration best objective is smaller than so far the best one. Okay, so we aggregated these two conditions in a block of code. So only this situation happen, we update so far the best solution. Gene wise copy. Make sure you do that. And objectivity within this block. Okay, so that will make your life better. I mean, without complicated structure, check if optimization, maximization, minimization, such kind of things. What you need to do is that during this function, you need to compute iteration average, find the iteration best, and then check whether the iteration best is better than the so far the best. If that situation happen, update so far the best solution. Otherwise, no any update for the so far the best solution and the objective. So you need to do that by yourself. Okay, so I'm not going to do the code for you. So let's go back to the one iteration. So basically, we perform crossover, perform mutation. After that, we update so far the best solution. And then, because right now in our code we have computed set fitness from objective variable. So during the perform selection operation, we don't need to code it again, right? So we kind of comment it out. So let us go back to our assignment. So I will repeat the procedure again to let you understand. So initially, we reset initial population, right? It doesn't matter whether it's reset or initialize. So during the reset, we initialize the initial population, we compute the objective value. During the crossover operation, we compute this part, we compute the objective part. During the mutation operation, we constructed this gene chromosome, and then we compute the chromosome. So after that, we firstly computed the fitness value right here, and then in update so far the best solution, we look through each chromosome, identify which one the best ID, right? Is the best, right? And also we look through objective value, right? Actually, we also look through the fitness value to see which one is the best, which one has the largest fitness value. So that should be the best ID. So after that, we will check the value, check the objective value. We'll check the, suppose the ID is right here, we check the objective value. Comparing comparing this guy, well, if this is the best one, we check with this guy, and then we need to set up the condition. If it is maximization problem, and the value is larger than this guy. If it is, otherwise, if it is the minimization problem, and this value is smaller than this guy, okay, we update so on the best objective value and also the best solution. That's what we have done in so-called this function, update so on the best solution. All right, after that, we will conduct the selection operation. So during the selection operation, we kind of take advantage of this indexes array. So the purpose is that you need to either way stochastically or deterministically set up the indexes, the candidate index from this list, right? So right now we are doing the selection operation. So we need to choose the ID or the fitter chromosome, right? So we need to write the ID in this array. So in deterministic selection, simple, because deterministic selection, what we need to do is that we sort the target value, the key array is right here, fitness value, and that's the ID's array. So we ask the array help us sort up to this place, so that the fitness value start from those ones. So those one probably is 0, 1, 1.5 up to 0, and then the corresponding index has been sorted right here, right? But we need to choose the maximum fitness value. So we need to reverse this area, reverse. You don't need to reverse this fitness array, in the deterministic selection. You don't need to do that, because what we need to assign is that we'll pick up the best one. So you need, after the sorting, the best 10 should be remain here. So we kind of reverse it. So after the reverse this index, we get the best 10. For the example, we will get the best 10 IDs right here. So that is for deterministic selection. On the other hand, if that is stochastic selection, we need to stochastically set 10 index in this array, right? So that is for stochastic selection. And stochastic selection, you don't need to need any data. You simply reuse this fitness array. So how will you do that? So as you can see, so we add up the fitness value, this kind of algorithm. So up to this total index, so we get the total value, and then you conduct 10 times. In this case, we conduct 10 times random number generation, and we type it up with this maximum value, and then during each stochastic selection, we need to check the value, check the stochastic value. So that should be theta times total sum, right? So we check so right now, if we add it up with the previous value, that turned out to be a threshold for this index selection, right? So we go through this place, okay, bingo, right here. So pick up, maybe this is A, so we write the index right here in the 0th selection in the first one, so probably pick up here is 14. So that is the procedure we conduct the stochastic selection. During this iteration, we kind of assign 10 index. From this, well, you can call it this is relative wheel. So basically, that is relative probabilities, and we add it up to set up the threshold for each item, right? So once we get the random number, we time the total sum, and we start from zeros and one by one to see if the value is stuck in this place, and this guy is chosen, and we write index layers. So after we construct the index, right, the rest should be the same. So right now we need to go through with this index right here. Suppose the index is 10. If it is the stochastic selection, probably 10 will appear twice or more than twice, right? So 10, 10, 10, and means suppose this 5, 3, 4, 15, 10, again, 8, 1, 2. So probably the final index will appear. So what you need to do is that start from the first one, 10, right? So pick up 10 right here. Copy gene-wise, copy each gene to this place. This is the 10, right? Also copy the objective value. We are not going to recalculate the objective value again. So copy everything, right, to this place. And then this is the zeros one. The first one is 3. 0, 1, 2, 3. 3 is right here. So copy all this gene and objective value to this place. In the second, 10 again, right? 10 again. So we can do here, make it the gene-wise copy to this place again. Gene-wise again. So after we copy or move, actually it's number, we simply copy the gene value to this so-called selected chromosome array. Then we need to copy them back. So zeros line come here, first line, second line, third line come to here. We copy everything back here. Also, we copy object value back to this object value again. So that finished one iteration completely, right? So after the first iteration, definitely there should be certain value, right, which has been assigned previously in the previous iteration. It's okay. Because start from that point, we kind of reshuffle these arrays, start doing the next crossover again. As you can see, we keep reusing this array for our GA operation. There should be no any extra data required, all right? So I did not mention about the mutation. If it is a gene number based mutation, we have another flag there. So just check about the operation. I mean, if you understand the procedure and if you understand the data structure we have been using, you should have the right implementation. Okay, so what has been wrongly doing in Rachel's project probably is perform selection operation. Okay, stochastic selection. You need to check it out by yourself, okay, Rachel, right? So deterministic selection, okay. But this place is not correct. So as I say, we need to copy the chromosome, selected index, right? So, okay, back to the selected one. But after that, we need to copy the selected back to the chromosome. So that this is the place you make it, you did it wrong. Did you see that? All right, so that's a chromosome, right? So that's one by one copy, chromosome. I, J, exactly equal to selected chromosome I and J. That's it, just one by one copy to that place. So that will make it the a copy back correctly. So again, objectivity. Selected. Not index side. As from that point, it has been done. So we are not going to check the indexes again anyway. So index is just for the selection. We either is deterministic selected or stochastic selected. The index has been put in this array. The first population size index there. So we want to copy to this temporary array. So then we copy that back to our parent. So for the next generation, for the next iteration. Okay, so well, so that will finish the computation, right? So run one iteration. So basically, just perform cross operation, perform mutation, update all the best, perform selection. So that's it. That should be the correct procedure for conducting the full GA operation. All right, so I ask you guys to just play around a little bit about this kind of data structure things, knowing what you are doing and what you have compute or assign any value to this array, what are they actually doing? Okay. So remember that don't use new operator in any function. And I also see some. Oh, okay. One more things right here in your main phone. So in your main phone, you kind of prepare the problem, right? So if you need it, if you some of you do add the problem related to control to the GA monitor. So this is the GA monitor. The user interface will be solely belong to the GA solver. Okay, so there should be no any problem-dependent UI control here. So if you have problem-dependent UI, you need to do it by yourself in your own main phone. Okay, so so basically, in your main phone is that you kind of determine in here. You will determine, well, for a job assignment problem, you model that problem as a list of 0, 1 valueless integer, right? Okay, so in that case, you kind of encode your solution as a list of binary value. So then it's essentially a binary GA. And also you need to provide a function. Setup time is not right. Well, we are not calling. This is objective function, right? So GA will prepare a list of bytes standard for represent a solution constructed by the GA for you. You need to evaluate. You need to decode it. So I'm not going to say it's irrelevant with setup time. So it's kind of get objectivity value, get objective value for a solution. So anyway, the name is the function is totally defined by it. But what you need to provide is that you need to decode, right? You decode the gene, the chromosome. Well, it is generated by GA for us. Decoded the chromosome generated for us into a solution of our problem. So remember that this function is the only interfacing function with GA solver. This function will be repeatedly called by GA solver, right? So within this function, do not have a new operator right there. Okay, so this function just simply serve as the function that you decode a solution prepared by the GA into your problem's format. So since right now in your job assignment problem, probably you like to represent the solution as a matrix, right? So probably you should depend on well, I might call it current solution. So you prepare that, you allocate memory just one time. So where should you allocate that memory? Once you read in a problem, right? So you did not provide a function, right? You did not provide. Some of you did not write the function to read in the benchmark file. So once you read in the function, probably you can generate dynamic. So generate your problem dynamic right here. So after that, you it's not good at all. Yeah, number of job, right? So number of job. So after that, current solution new int number of job times number of job. So in certain kind of in a certain function, once you read in once you read in a problem, your benchmark problem, or you dynamically allocate a problem in your main form, you will instantiate the memory for this current solution. All right, just make it that memory allocation once. Don't do that in your objective function. So let us go back to the objective function again. I call it get objective value, right? So objective value here is a solution. Well, I think it's okay. I mean, so from now on, the penalty factor is not in your GA, so that should be defined in your main form because the main form stands for that penalty factor. So probably you need to have your double value penalty factor here, penalty value there. So simply times your penalty values if your violations, and then again, you see if you have violated the constraint, that's sum. All right, so don't use that. So I know you guys need to calculate the row-wise violation amount, right? So you put that in an array. So again, that array is all similar to the current solution. It's related to your problem. So I say that I mean your scheme I mean is totally not correct. So make sure you operate. Actually, what you need is just make sure this function is work well. Get objective value here. Okay, you decode it. So probably you will decode it. You will decode that. You can decode it to current solution. So the row-wise violation amount can be computed from this array. So each time you get a solution, just transform this array into current solution 2D array. And then calculate violation amount row wise and column wise. Because right now, if you convert that solution one dimension into this two dimension, you can set up nested for loop, right? To compute the value right here. With it, just check the value of current solution, which is converted from a solution. So you don't need to never add a new operator in your objective function. Okay, so you need to do that by yourself. Okay, so try to make your objective function calculate correct value back to the GA. Okay. All right, so I think I will end up right here. So make sure, I mean, you correct your genetic GA solver. All right, and resubmit your assignment 8 again because it's okay. I mean, what you need to do is just update, just correct your genetic GA solver. So make sure the genetic operation work well, work correctly, and then you can plug in your permutation GA nicely without any problem. But if your permutation GA also involved a lot of problem-dependent stuff, make sure you move that out. Move your move your problem-dependent data out from your GA. Okay. All right, so I will end it up for the discussion about assignment 7 right here. So if you still have any question, probably you can check me, catch me sometimes. Okay. All right. So let us take a break. Then we are back for the new assignment. All right.
就加一个选项，问他要不要加。
没有，我没有批判你的价值，我称赞他没有价值。他怎么样？我知道是第一讲，跟他说，对啊，这个也没有啥价值。跟你成大毕业的。
Okay. We are back for assignment 10. Assignment 10, you will be very happy for that because the PSO meta user algorithm is so simple, right? So once you finish the GA and finish the ACS, definitely PSO is just a piece of cake. So you can just finish that assignment probably within 1 or 2 days. Really, okay. So data structure wise, it's quite similar to the ACS method, right? So well, basically that should be the comma for all the meta-heuristic algorithm. We always has a population of solution agent, right? Try to evolve this solution toward the ultimate solution. So data-wise, it should be similar, right? But the problem is right here. We like to have an application that can solve several benchmark problems. And as you know, the benchmark problem, since it's the continuous optimization problem, right? So user need to specify the objective function. So user needed to do some coding. In previous time, there is no way to let user type the code. Okay, type the code. So for example, Fortran or code or C or C++, and then compile it during a runtime. In previous, if you like to solve the optimization problem, you need to go back to the Excel, so-called spreadsheet. Because the spreadsheet application, user can define arbitrary objective function there, right? But fortunately, in Dynamic Framework, actually, in your application, we can employ compiler dynamically or runtime compile a code prepared by the user. Right, so we can let the user arbitrarily specify their objective function arbitrarily. Okay, so that is the way we dealing with different kind of optimization problem, because that problem should have their own formulation of the objective function. So it's very hard for you guys to implement that interface to let the user write a C# code or VB code and then invoke the compiler, because a lot of things needed to be done there. So I kind of wrap up that functionality into a library for you to the user specify the objective function arbitrarily. So in this assignment, I will show you how to use this library to read in the COP, so-called continuous optimization problem. So later, but before that, we will prepare class, particle swarm class, for solving continuous optimization problem, right? Okay, so maybe let us just prepare as project skeleton. All right, so we close solution, and then we create a new project. So that will be assignment 10. Windows Phone Application Dynamic Framework. So next step, set the desktop. And then we coded the research 09. Assignment 10, PSO, particle swarm optimization system. Solution, edit. 4.7.2, okay. Sorry. So similarly, similar to the previous project, we let the UI play UI throw, and then we will design our solver as a solid class. So in the project, we add class particle swarm. Optimizer. You always use a name phrase, a noun phrase word to name your class. So particle swarm optimizer. Fine. Edit. Problem-wise, you don't need to worry about that because I have a library for you. So structurally-wise, well, let me quickly change the file name mainform into mainform.
老师，你有记得录音吗？
好，我再查看一下。
谢谢。
有了，那个麦克风在叫。好。Okay, so since it will be used, probably will be shared by other projects, so we make sure that it's a public class. And I think I have a demo application for you, so check out that package I provide for you with your assignment. So we have instruction right here, right? PDF file. And also I have a benchmark problem for you. So this benchmark has been wrapped up within this subfolder, COP benchmarks, this subfolder. Each problem will contain two files. The extension is .cop, the other is RTF. Actually, it's RTF. You can see it, double click it, and then by default it will invoke Windows form. Windows Word application. So we call you guys are familiar with this extension, rich text format file, right? So we can add graphics, we can add some different kind of data from different kind of applications. So actually this is equation, right? So we can insert equation, we can add equation in a rich text format file. So definitely no problem. So as you can see, each problem there will have two files. The RTF file do describe the title of that. For example, let me show this one. This one will be tested by your application Peak. Peak is a famous two-dimensional automation problem. I mean, originally it is available in MATLAB library. So it's kind of complicated objective function, right? But it's two-dimensional automation problem. So equation right here, we try to minimize this objective function. So there is no any extra constraint. We simply have a range constraint only. So x, y within this range, -4 up to +4. And since this objective function is differentiable, so we can get a gradient vector. If that function is differentiable, then we can use hard computing method to solve it, right? So probably you guys are taking the course of optimization, introduction to optimization, right? So you might be familiar with some hard computing method. So once your objective function have a gradient vector available, you can use that method to get, well, I always call it as a local optimize. Definitely, you can. Once you specify the initial point, you will get local optimize quickly, right? In hard computing method. But right now we are using the particle swarm, which is a meta-heuristic algorithm to solve the problem. So you are not going to expect that every time you will get the global optima, right? So if the problem is complicated. But right now the problem is simple. This is just two-dimensional. But this benchmark problem is famous because we have obviously we have three. I think we have three local optimas there. Only one is global minimum. So this problem information has been shown up in this rich text format file here. So we try to minimize this objective function, and we have the gradient vector available, and we know there is just one optimal value, -6.5511. The solution is right here. So this is the best objective. This is the best solution. Okay. So graphically we can represent as you can see, this point should be the global best. So each benchmark problem, this format is totally designed by us, by my lab. Okay, so it is not it's not a standard format. So make sure that this kind of benchmark problem is designed by us, by my lab. So, and if you look into the .cop file, it's a text file. You can use notebook to open it. All right, so some text file you can see. Title, pick 2, type. So definitely there is certain kind of label there, right? So minimization, type minimization, dimension 2, lower bound, enumerator. Enumerator meaning what? Meaning each dimension will have its own lower bound and upper bound. So -4 up to +4. So this is the first dimension. You can say that x coordinate, y coordinate, fine. So number of optimal solutions. So some benchmark might have multiple optimal solution. All right. So we just have one optimal solution. The solution is right here. How about objective value? Objective value is -6.511. Right. Well, another one is number of linked assembly. If you have your objective function and gradient vector compiler as a DLL, you will see it specified right here. But not in this case, not for this benchmark problem. So the problem right here, we specify the objective function in C# programming language. So as you can see, this is C# programming language. And probably within this computation, it's very complicated. You might have, you might define certain kind of global or variable. If that case happen to your benchmark problem, you might see some C# code within after this label, global definition. And also, basically, user need to provide code C# because it's a C# code. Another option is that you can use Visual Basic VB. Or VB can, if the code is written in VB, you will specify VB right here. But right now it's in the C#. So you can have code defined within this global definition function. You have actual code in initialization function there. But most importantly, at least you need to have code special after this label, objective function. So objective function, you think about that, you kind of provide objective function, right? So what you take in is an array, double array. So right here, the name has been fixed into X array. So right now, since what we are dealing is two-dimensional, so the element-wise you can access just x0 and x1. So during this part, just try to complete the computation of this complex equation. Okay, exponential x squared y squared, right? So and also we have x triple power. So there, so you can see. Objective value, well, we have local variable special 1p, 12, x3 times y3. Anyway, you should check it out. As you can see, math that exponential, right? So it's a pure C# programming code, right? So you need to make sure everything is okay right here. It's my calculator. All right, so this is the objective function. Finally, you need to specify this way. Objective value is a keyword. It's a variable keyword. Objective equal to this one. And how about a gradient function? Gradient function will return a vector gradient. So G is the default data structure. So never mind, COP is in text format. And within this text format, user specify its objective function in terms of C# programming language right here. All right, so once we read it in this benchmark file, I will invoke C# compiler to compile this code during the runtime. And once it's compiled successfully, it can be linked with our application directory. So let me show you how to open this file. All right, so this is the demo application PSO for COP. And as you can see, some benchmark two-dimensional problem, so we can see the objective function three-dimensional graph there. So again, this application will use T-chart to display this to display the objective function. So this executable code needs this dynamic link library. So let me run it for you. Okay, so this is the demo application. So if you implement a real number encoded GA, you can compare the efficiencies of GA and PSO in your project. Okay, and as you can see, we always will have this progress line chart display, right? Iteration average, iteration best, so on the best. Yeah, you need to allocate this chart once again. So if you think about this kind of meta-heuristic algorithm, GA and corner optimization, PSO, they are all the same, right? The methodology-wise, they are the same. We always employ a population of so-called solution agent, try to evolve the solution, right, toward optimality. So we need to monitor, we need to check the progress on iteration average, iteration base, and so on the best solution. So finally, we will give the user the so what the best solution as the final solution for the user. Okay, so open a benchmark. So I need to go to this benchmark library here. So let me select. So the naming wise, you see a pair of parentheses, right? The number within this parenthesis means the dimension of that problem. So actually, we have an example of 2 dimension. Another is 30. The dimension is 30. It's a large problem. So if you look into the peak, it's just 2-dimensional problem. So it's simple. So once we read in that benchmark problem, well, as you can see, whoa, a bunch of controls showing up, right? So this is the display control for this benchmark problem. And this panel is used to display the objective function. So right now, since it's 2-dimensional, objective function is a 3D surface on 3D space. So you can see it's a minimization problem. Dimension is 2. We have the same bounds, upper bound, lower bound, right? So we have what number of optimization solution? Just one. Objective value, best objective value. Solution is right here. And as you can see, what is this control? Rich text box, right? So rich text box just show the content of that RTF file. The RTF file we just show, right? So remember that this is the rich text box. Rich text box can show all the content of rich text form right here. All right, so it's nice, right? We don't need to create this user interface, this control. My library will help you to display that. What you need to provide just panel, another panel, to illustrate the detail of that benchmark problem within this panel, and then show the graphics within this panel. What you need to provide is just, well, invoke a certain kind of function, and then that benchmark will show up its related information within this panel. So solution information is totally designed by you. You have to check the solution evolution condition, so you kind of prepare this user interface. So this user interface is not provided by the by the benchmark problem, because that is related to your PSO or your GA, right? Okay, so we have this problem ready. So right now we have problem ready, and then in your main function you might employ a solution solver. For example, PSO or GA. So either way you can select it. So if I select particle swarm optimizer, create solver extension object, right? So first. So again, probability, right? Probability show up. Those parameters can be specified by the user of this particle swarm optimizer. So iteration limit 100. And if you have gone through the slide, you know there are just 2 parameters that can be specified by the user: cognition factor and also social factor, right? Another most important parameter should be the number of solution agent. Right now it's a number of party, 10. Very small scale problem, so we kind of employ 10 parties to solve the problem. All right, so user can change that. If you like to change to 20, right? So for now, I just set it to 10. And this factor, particle swarm, a particle will move current particle to another new position based on these two factors. One is referring to its previous experience. The other should be referred to the global experience, right? So one is the social factor. So right now the factors are even. So half of the probability will refer to the itself, and half of the solution factor will depend on the so far the best solution. That's it. So the parameter-wise is so simple. I mean, the particle swarm is the most simplest meta-result for solving continuous optimization problem. Well, it's simple. So it will not be good enough, okay, for you. So we reset. So reset everything, right? Reset the initial solution. Reset, another reset, another reset. So right now we have 10 particle represent 10 solutions right here, exactly on this three-dimensional surface. So the solution is right here, x1 and x2, right? So each point is exactly the solution of that particle. So right now we try to evolve iteration by iteration, right? So this 10 particle will move to the new, within one iteration, they will move to a new position. That means evolve to a new solution. Right here, we regard it as solution as the position of particle. So run one iteration, every particle will move to its new position, right? So that will complete one iteration. So we needed to, again, calculate the iteration average and find the iteration best. And if the iteration best is better than so far the best, replace it. That's the operation is the same, exactly the same as the GA, as the particle, as the ACO. Okay. All right, so we're on another iteration. Particle move, right? So far the best solution is not updated. Currently it should be minus, maybe near minus 2, right? But the best objective value is minus 6.5511, right? So run next. Oh, okay, it's improved, right? So you can maybe it is hard for you to see it. But you can check. Well, the global best is right here. Currently, the particle distribution is right there. So for two-dimensional optimization problem, actually you can see the movement of this solution agent to check whether they are kind of together within a local optima or global optima. So you can check that graphically. So run one, another iteration, another iteration, another iteration, another iteration, another iteration. Okay. Nothing improved, right? Okay, let me ground to end up to this condition met. This is particle swarm optimizer. No any improvement for the so-called result. Again, but because it's meta result, so you cannot reset. And run again. Wow, it's okay, right? So the current best solution is up to 6.5473. Well, it's close to 6.5511, right? Oh, okay, not bad. So all the point has been converged into this solution near the global optima, right? But some particles still remain there, right? Because as you can see, there are another two local optimas there, right? One is here, the other is there. We set run again. Not bad again, right? 6.53. It's a little bit, difference from the 5511. All right, so we set run to end. And since right now you have a rich user interface, so once you finish the project, you need to try yourself. To try to change certain kind of parameter. If I just employ 2, what will happen? I just employ 2 particle, 2 solution agent to evolve this best solution for me. Can I get it? Run to end. Well, even though it's not bad, but again, it kind of stacked there, right? There's no any improvement or so on the best solution. So still, there is a distance from the global optimas, right? Reset, run to end, try it again. Wow, this time, both of them stuck on local optima, right? it is far from the global best, right? All right. So compare that with your GA. So I encourage you to implement a real number encoded GA. So create solver. So new object will be extension. So similarly, if I set the probability to 10, iteration limited into 100, the same stopping condition, same number of population, right? Number of cut just one number of cut. So we set 1 to n. Still not good, right? So as you can see, since what we are dealing with is so-called meta-heuristic algorithm, so it is not guaranteed that the final solution is global optimal. But this time you can see the value we obtained is 6.5507. It's really close to the global best, right? So we run it again. So since we are using so-called meta-heuristic algorithm, so a lot of stochastic process has been conducted within this operator. So usually, if you want to make any conclusion, you need to run the evolution more than one time. So probably at least maybe 20 times or 30 times, and then get the average to represent the behaviors of your method. Okay, so we are not going to just run once. So usually you will set up a stopping condition, maybe run the same problem for 30 times, and then get the averages to show the computation capability of your solution. Okay, so that is what we like to achieve. So again, user can choose spiky. All right, so a lot of benchmark problems are frameworks because they are designed by certain scholar of expertise. They try to challenge the optimization method generated by the researcher. So this problem are really tricky. So a lot of local optima has been special, but it's two-dimensional. Well, it's weird. Since it's two-dimensional, so why global? It's deviated from this service. I don't know. Let me open another one. Peak. Okay. 6 hum camera. So in this case, in this benchmark, there are two optimal solutions. So objectivity are the same, but they are located in different locations there. So it's symmetry. So another one there. And we can employ PSO reset not to end. It's close, right? 1.03. It's close, but the point wise is a little bit deviate. If we run GA reset not to end. Okay, similar. So once you've done it, you should try some large scale problem. For example, accuracy 30, dimension is 30. So in this case, if the dimension is larger than 2, it's meaningless to take a look at this figure, okay? So right now, the objective surface is 30 dimensional. So right now we just project, we simply project so the objective surface into these two dimensions. So it's meaningless. I mean, if you look into the position about the global optima and the particle position, it's meaningless. So if it is high dimensional, which want to check the efficiencies of this method. So usually, if it is large dimension, for example, if it is 30, so usually normally we will employ, we will enlarge the population size, and then you can try. If I simply set the cognition factor larger than the social factor, try to see what would happen. Okay, so you can see particle swarm, they converge to, well, actually that should be a local optima quickly, right? So right now the best objective value should be 0, but right now it's stuck on the 15. And if you look into the GA, if I again set into 30, probability 30, we set 1 to n. Usually we will check this progress of so far the best solution. As you can see, our GA is still alive, right? So it keep improving, keep evolve the so far the best solution toward the optimality. So this kind of shape of this so far the best objective value reflect the liveliness of your solver. So once you've done it, you had better just try to run several examples to see the behavior difference between GA and PSO to get much more insight characteristic of this meta-user algorithm. That will be helpful for you. Later on, if you bump into a complicated problem, you might think, well, should I use PSO or should I use GA? But roughly, GA will be better than PSO in solving high-dimensional optimization problem. So make sure you understand that. And you can get this evidence, well, just run comparisons between these two methods using your application. Okay, so that is what we like to have. So we like to have PSO. And if you have a real number GA, you had better use that, add that, implement that into this project for comparison. Okay, so how to use these algorithms? So right now in your project, so let me go to the file location. So this is your project, right? This is your solution folder, solution file, and the project file. So within this solution folder, I would like to add, again, excuse me, made a mistake. Add a folder. I like to call it DLL use. DLL use. So copy the DLL that I gave to you. So the DLL is right here. So you need to copy 4 files. One is called benchmark DLL, and the documentation is right here, XML file. The other, because we like to display the 2-dimensional objective function, right, in 3-dimensional space, so we need to we need the help from the T-chart. So copy these 4, DL and XML. Copy that to your DL4. So right now you have all the executable and source code ready for your project here. And probably you you don't need to copy the whole benchmark into your solution. Otherwise, if I download your project, everybody has this way. It's really troublesome for me. Okay, so but probably, well, at least you should check the. Well, never mind. You just keep that folder outside your project, right? So I may call it desktop. So I simply copy that into desktop. So later on I can open that quickly. Okay, so mostly important things that you need to learn to use this COP benchmark DLL. All right, so once we add that DLL to our project, so right now we can reference it, we can refer it. So within your project, click on these references. So we add a reference, and then browse your folder to not here, desktop, this solution, DLL used. So what you need to specify just this one, COP benchmark will be okay. Compiler, once compiler compile your project, the compiler will add a t-chart to your bin directory automatically. So basically, what you concern, what you are doing, what you are dealing with, just this DLL. So added this DLL will be okay. T-chart will be later added by the Visual Studio for you. So your project refer or reference this COP benchmark. So let us quickly take a look at what class has been defined or what data type has been specified, have been defined, has been stored in this DL. Double click on it. So you will see here COP, Continuous Automation Problem Benchmark. Click on it. So there is a namespace COP. Within this namespace, okay, we have COP benchmark class. This is class. We have a graphics user interface display. We have COP problem, Objectivity display, problem editor. We have enumeration, optimization type. Yeah, definitely. Well, automation always has maximization, minimization. Okay, we have a selection option, programming language. Programming language probably just C# and Visual Basic. That's it. All right. So we have the most important class should be the COP benchmark. Okay, we know that. So let us quickly look into this this class constructor, right? And some of them you cannot see it clearly, right? So never mind. Let's just directly use it, and we can check out the available function and the properties of this class. There. Okay, so in your main form, since right now we have particle song optimizer, right? So later on we will populate that. So probably within this, within your main form, we will to make it a commercial-like application. So usually you will have menu strip. So menu strip automatically dock in the top, and you have a tool strip, and you have a status strip automatically dock in the bottom. So spray container, and then probably you like to have a spray container, but the orientation, well, it's totally up to you. You can design a good one, but orientation. Okay, so suppose I like to display. The idea is similar to the generic GS of what we have done in the. So this panel will be used to display the problem, benchmark problem. This panel will be used to display the objective value, which will display the t-chart right here. So suppose that is the idea. Split container 2, panel 2. This is split container 1, panel 1. Fine. There. So we will employ a button, right? Well, never mind. We simply click on this button, add a button. And by default, button will show up graphically. So in display style, we have that, and also we have text. So we will prepare a text to let the user know what will go in, what will be going. If the user click on this button, open, try to open a benchmark. Okay. So how can we open a benchmark and show it up by using this DLL? All right, so double click on this 2 or 3 button. Name wise not good, so I call it 2 or 3 button. Open. Double click it on here or subscribe its quick event. All right, so usually you need to add the open file dialog, right? Open file in there. So, but right now, since everything has been wrapped up in this DL, so you simply search the functionality provided in that DL. So let me ask COP, right? Okay, so COP is ready. Dot COP benchmark. This is the class, right? But probably I hate to add this namespace, so I simply say now, okay, COP benchmark. But it's not recognizable, right? So we just should add that using statement for us, using COP. Because right now we have reference COP, right? We have COP benchmark DL reference. So right now it's recognized. So at first, once you have a class ready, try to see what kind of static function provided by this class. So okay, that there. Wow, a bunch of static function. We don't need to instantiate any problem object right here. So create a new problem and show editor. Well, okay, you can try that. And as you can see, I kind of add a so-called targeted comment in each class in definition and each function. So you can see these, this kind of intelligence information is provided by that XML file. Okay, so if you design a good library, you should provide all these targeted comment there. To create even, what we need to probably involve this one, load a problem from a file. Load a problem from a file, because we benchmark a problem, right? So once this function is called, you will get an object of COP benchmark back to you. Okay, great, sounds great, right? So this function is called, right? And then we will get a benchmark. So in your main form, definitely, you need to prepare an object COP benchmark. I might call it my problem. Fine, problem there. So invoke this function, you will get your my problem. Sounds beautiful, right? So let us try it. Okay, so click on that. Open. So extension shows COP, right? So this has been designed. So this dialog box, you don't need to prepare for that because this static function provided this interface dialog for you. So we need to navigate to desktop COP benchmark there. I have copied that already here. So if we click on the peak, nothing happened, right? But okay, because right now you have my problem ready there. So believe it or not, let us do it again, right? So I set a breakpoint there, right? So if I click on the button again, it's about to execute this function F10. Show up. This time I might choose actually 2. Okay, this time has been executed, right? So move your cursor to my problem. All right, so my problem has been instantiated, right? So a bunch of data there, description, and dimension, two dimension, file name, file path, you see, COP, and summarization. How about optimal solution? Okay, optimal solution, you can pick it up from this property. So you can display the information of this problem manually by providing, but you don't need to do that. Okay, so up to this point. So let us check. The first try is that we kind of use this class, right? COP benchmark is a class. Try to access all kind of static function. She show editor to edit a problem, validate those reference, display a problem on panel, display objectivity. Well, okay, we might have this kind of ability. But once my problem is allocated, let me try to use my problem. This is the object reference, right? Try to access what kind of functionality or property of this problem I can set. You can get the best objective value. You know coding language. Okay, you know the dimension. So if you like to look through everything, you will use this object dimension right here. Okay, again, the similar function has been shown up. Display objectivity graphics, display on panel. display solution on graph. So just look into this explanation. So in here, if I want to show my problem displayed, my problem displayed on panel, so what you need to provide is just panel. Okay, so primary display container one dot panel one. Okay, this is the place. I'd like to show the problem on this panel. Nothing returned, right? So okay, simple, right? Open again, continue. This time I choose peak back again. Peak 2. Open it. Alright, bingo. The problem information has been shown up right here. Problem is peak 2, blah 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 there. Also we have okay, rich text format. And speed container, another one has been added right here. Alright. So that's the way. You take advantage of that library, right? That DR library, right? So okay, so you have problem ready there. So okay, sounds okay. And how about the graphics display? Okay, similarly, so you look into, okay, this is the panel 2. Right? So look here. Again, this is my problem that display Objectivity graphics. So display a 2D surface on 3D graph to show the projection of the Objectivity onto two-dimensional space. Usually this is to display dimension 2. Okay, let me show you. How about another function? Display solution on graphics. Display the current position of particles on the Objectivity surface. Okay, so probably you will invoke this one. So later, but so right now you do not have a solution, right? You do not have a solution. It's double, right? So let me just show the problem. Display Objectivity graphics. Again, it will ask another panel. So fine, the panel. All right. So split container 2, panel 2. So let me remove this breakpoint, terminate it. So peak again. Okay, everything is there. Since this benchmark problem has one optimal solution, so this solution has been shown up right here. So as you can see, it is familiar, right? It's a T-chart component. So everything you can set the color, middle color into different one, point color, optimal solution color. No, you cannot set it. All right, I refresh it. All right, so everything is already there. I mean, it's for your problem. So the problem is that how can you employ PSO solver to solve that, to solve my problem, right? Okay, so let us back to the particle song optimizer. So since right now it's a particle song optimizer, and we use this kind of phrase, position, right? Or particle position. So probably we'll start defining the data structure for particle song. So what do you need to have double, right? Since we are BLE. Array or array. You might call it solution again. Fine. Which is similar to the ACOS, right? ACS, right? Or probably you might call it position. Never mind, I might call it solution. Well, actually, you can copy all those codes from ACS came to here. So similarly, we will have what? Double objective value. Objectives, right? And we have also have what? We have also double. So find the best solution. Similar, exactly the same solution, right? And we also have double. So find the best solution. Made a mistake right here. So what the best objective? We don't know. We don't care means for a particle swarm optimizer, we don't care it is maximum value or minimum value, but definitely we will ask the user tell us optimization type. Optimization type probably, well, because right now the particle swarm optimizer is located within this solution, and this solution we refer to this COP benchmark, right? So we can using that COP, using that space. If I use that in my particle swarm optimizer, it's not good anyway. But again, you can define your own enumeration for maximization or minimization. But right here, I kind of take advantage of this enumeration optimization type, which has been defined in COP. Okay, OP type. Never mind. I mean, you can always specify a good name for it. Optimization type. Probably I will give it the initial value minimization. You see, in the benchmark one, we have minimization and maximization. Another automation problem is called goal matching. But right now, by default, selecting to the minimization problem. Okay, so I have OP type ready. And definitely, you should have a dedicated specifier, right, for objective function. So, what kind of objective function you expect in order to evaluate the objective value of a particle? All right, so with the I don't think a COP have this kind of delegate, right? We don't have any delegate. As you can see, we just have an enumeration and a class. So you need to define your own delegate. All right, so maybe in the end of this function, public delegate. Then after the delegate, you need to specify the function return type double, always return double. And I call it OBJ. Okay, COP, OBJ is objectivity function. This is the name, dedicated name. And then it will took double array. So if I give you a double array, that means a solution. And that function will return objective value back to me. It's the same. I mean, it's just, if you look back into GA and ACS, we definitely need this kind of delegate. Okay, so we have delegate specifier. So yeah, it's about the time. Solution-wise, we also need what? Because it's a real number optimization problem, right? So we will ask the user needed to give us lower bound, right? And also upper bound. Right? But as you can see, particle swarm, not just solution, right? So suppose solution I, meaning what? Particle I, right? It will construct this solution. This solution actually is called position, right? So each particle will move to a new solution, and then each particle will keep its own best solution, right? So we might call it double self best solution. You know what I'm talking about? Because each particle will keep its best solution or its best position. So that is the spatial data structure required for particle swarm optimization. Okay, so not just that, objective value is the so we also have self best objectives, right? So these are the actual right? So we always have so far the best objective, excuse me, that should be double, so far the best objective, right? So far the best solution there. And for the particle swarm, we have a special parameter, I might call it self factor. So initially it's into probably 0.5. So E double social factor. I'm not going to cover everything for you, okay, but roughly we will design. Okay, so the rest probably we have iteration ID, iteration they are the same. I mean, like the GA and the ACS, but public interface functions, void, public, void, reset, right? We always have the reset function there. We said we need to reallocate memory, which are related to population size reset, right? So, but most of them should be memory should be allocated just once in the constructor, right? So this actually definitely we need to reset that. I mean reset function, and also public function wise we have a public void run same one iteration. So you need to refer to the previous meta user algorithm to conduct this one. Public void run to end. These are the most important public function. But within this function, we should run one iteration. We will have what? I might call it move all particles to new position. If you would like to use this so-called position, then probably you will change the solution name. Okay, name. You know what I'm saying? Okay, it's totally up to you. But extreme positions. This is the way, right? Fine. Now we make this naming consistent. Position, move new position, right? So current position, and then self-based solution. Now we are calling self-based positions. Well, it's totally up to you, never mind. Okay. If you regarded a particle as a solution, I might stick on the solutions, and then the self-based solution is totally up to you. Right now, since we are talking about a particle, so we keep using this position name. Fine, move all particle in new position. And then after that, what do you need to do? Update. So from the the best solution. Right? That's it. This for particle just these two primary steps will be executed, right? More particle to new position, update so far the best solution. That's it. Right? So you need to do the rest of the coding by yourself. So probably you have an iteration ID, right? And the iteration limit. And you need to declare public property. Okay, for those parameter, PIME modifiable. All right, so you need to do that by yourself. Okay, I'm not going to calculate that. So, okay, how can you implement that function? Move all particle to new position. Update so far the best solution. You should do that by yourself, okay? Just make sure you just conducting one pass algorithm to get the average, right? First. So similarly, you will have the same, I mean, it's almost the same as the GA and the partition. So I will let you do that by yourself. So, well, you need to do that okay, by yourself. So finally, what we need to do? Move particle to new position. Well, I might call and I might rename it move particle new to new position. Okay, move particle to position. Update so far the base so another iteration. So well, it's depend on how you implement, because right now we roughly design two functions to achieve the operation of the particle swarm with the measure. But actually, I think if you like, you can merge both functions within one pass. You can try that. But probably not the case. You still need to move to new position first, and then during the update so far the best. So probably let me design this one. So well, we can use the factors and use the two factors and so far the best. Okay, let me change it again. So far the best solution. So far the best. So I'm gonna call it in. So far the best position. Yeah, to make it that consistent. Position, cell best solution, so far the best position. All right. Okay, great. So I'm saying that use the two factor and so far the best position. And the self best position to set new position for all particle. Right? So actually what you are doing is move all particle to new position. Right? So we are not going to evaluate the value. So if that evaluate the OBJ's objective is all new position and update self best position if new position is better, right? So each particle need to update its self best position if the new position is better than that, right? So update the self best solution and objective too, right? So we will always compare the objective value, right? So for each new position, we evaluate new objective value, right? So if the objective value is better than the self-best objective, then we will update the self-best position, right? So, and also, calculate iteration average and iteration best ID, right? So we look through everything and then find the best ID and then update so far the best solution and objectives if iteration best is better than so far the best. Okay, it's so straightforward. It's not complicated. Once if you have done successfully in GA and ACO, definitely this is just a piece of cake. I mean, for you to implement PSO. All right. Okay. So carry on the similar operation by yourself. Okay. So But again, you will see, wow, I need to lay out the chart again, right? And then prepare button, reset button, everything will be repeatedly. I mean, okay, definitely that is true. I mean, for so-called meta-heuristic algorithm, because that is a population-based evolution techniques used in meta-heuristic algorithm. So just carry out the same operation there. But most important is that if you want to display the current particle, right? So current particle, you need to get that from definitely from your particle song optimizer. So right now we have so far the best position, right? So we were encapsulate this data and then set a public property for the user to get it. So we have so far the best position, right? And probably it's not so important at all because we need to the best position. Probably is not. Probably we don't need it because we need to prop all the particle, right? So what we need is this position. Okay, so the position, right? So position we refactor through refactor, we encapsulate this position and make that as a particular positions, capitalized positions. So how can you use that? So right now, since we have position ready, right? So in our main form, let me quickly add another one. So we have we will add button. So reset, run one iteration. So what I'm saying is that how can you display the current particle on the chart right here, right? So we have chart so right here. So okay, let me try to complete this implementation. So button one here. btn reset. So reset is right here. And this one should be run one iteration. But before that, we need to instantiate btn create ESO solver. So usually that should be done in this button click. After this button is clicked, then this button is ready. So initially this button should be disabled, right? So and also we should need the help of property grid to interact with the user. So property grid. So you need to set up the docket by yourself. So I'm not going to do that for you. So probably because I need to use up space. So anchor that here. BBG solver. So if we add another object for the user to instantiate a GS solver, you can share this public grid for GS solver and particle solver. So you do that by yourself, okay? So what I'm going to show you is that try to instantiate an object and then reset, so you will see particle showing up in this figure. Okay, that is the mission we are about to finish. So create a PSO solver. So that means back to our particle song optimizer. So right now it's about the time we prepare the constructor. So add constructor CTOR security keyword, right? Hit tab key twice. So what kind of parameter should be supplied by the caller? First one, number of variable, right? So int number of variables, optimization type, right? GOP, oh, excuse me, because right now it's a real number optimization problem, so we will ask the user give us array, lower bound. Also, another array, upper bound. And then after that, COP optimization type. And the most important is that objectivity evaluation function, the delegate. The delegate, we call PSO, where's the delegate? Okay, excuse me, COP objectivity function, COP objectivity function, OBJ fun. Well, I think that's all. So particle song optimizer, again, this guy does not know anything about your objectivity function at all. You simply tell me, well, how many variables should I create? Definitely, that should be a real number, right? And you need to give me the lower bound, upper bound, and then tell me the optimization type, whether it is a maximization or minimization, and then provide objective function. Then I can evolve solution for you, get a better solution for you. That's it. That's the mission for a particle song optimizer. Okay, so one by one, number of variable. I do not have it, right? So okay, so I quickly create the data. Number of variable. So the name is exactly the same as the parameter name. So within this constructor, I needed to use this, that number of variable equal numbers of variable. This number of variable means this local variable. This one should be our data member, the number of variable. And also I have this lower bound, right? Lower bounds. Okay, I pick it up from your enter your supply the references. This upper bounds, and automation type. I needed to prepare that. Okay, OP type right here. So my OP type is showing OP type. Oops. It's my OP type. Pick it up from your type. Objective function, I need an objective function, COP objective function. Okay, I did not specify it yet. So I call it the objectivity function. It's a delegate, right? So objective function. So the objectivity function equal OBJ fun. So since right now you know the number of variable, right? So you look into your data structure, which one is dependent on the dense, solely on the number of variable. Not this one, not this one, not this one, because they are the size, the memory size depend on the population size, right? Okay. The population size, you might call it, well, later on, you might call it population size. If you don't like this name, well, I might call it a number of particle, fine. It's totally up to you, but from my viewpoint, they're just solution agent, number of solution agent, or you simply call it a population size. It's fine. So we set an initial value there. So again, you should define the property to let the user change that. So by default, I might call it 10. Particle number particle 10. So position depends on what? The size, the memory size depends on number of variable and number of particle, not solely on the number of variable, right? But the so far the best solution. So far the best position, excuse me. So far the best position. I will instantiate the memory right here. Once I know the number of variable. So number of variable. Don't screw it up with the number of particle. Okay, number of variable. How about reset? Well, if positions equal none, or positions get length. Excuse me, because it's a checked already, so I can delete use length. Not equal number of particles. So only in this case I need to reallocate memory. For those data, well, actually not reallocate, but in the very beginning that should be allocate memory, right? Allocate or reallocate memory, right? So position equal what? Position equal new double number of particles, because the user might change the number of particles, right? So for each smaller than the number of particles. Hypothesis. I kind of mistake, right? So it is not an array of double, it's an array of double array. Its position is an array, it's a one-dimensional array of double array. Okay, so each array I need to instantiate, but the size is exactly the same. I need to new double. The length is number of variables. So please, well, I need to. So you need to do it, but I'm not going to cover it. But here, the most important is that I need to allocate. Well, position is ready. Well, it's fine. Position is ready. So you need to do the rest of coding there. So, and also you need to set the initial solution, and probably you need to check the OP type. If OP type equal maximization, then probably so far the best objectivity equal double mean. Right? Else. Such kind of things, you check out the GA and it shows this, you will know what kind of data you should initialize, I mean reset. Oh, probably we don't need to, well, oh yeah, we need to reset initial value. So in reset, we also need to do what? Randomly assign initial position, right? And also evaluate, well, yes, randomly assign initial position. Update software version, you very objective is okay, so probably randomly assign initial position. And then we code it update software version. So probably you can do that during the reset. So in the very beginning, because before we proceed the iteration 0, we have everything is already there. We have initial position, we have randomly assigned initial position, and self best. Well, we don't need self best can be instantiated. I mean, within this update, so what best. Because so far the best, we also update the self best there. So once you complete it, you need to check the algorithm in detail, okay, to see everything is fine or not. So I'm not going to cover everything for you right here. So you can take advantage. Well, once you instantiate, so how can we randomly initialize the initial position? It's simple, right? So we simply loop through for int I start from 0 I number of particles, right? I plus plus. So positions for int j start from 0 to j number of variables j plus plus. Solutions, positions, particle I, coordinate j equal what? So we need a random number generator, right? So okay, add a random number generator. Random, ind new. So we have ind ready for us to use. So it was very simple. Lower bounds j's component plus ind next double, right? Times what? Times upper bounds j minus lower bound j, right? Okay, let's say position. Let's say so. Position is ready. So you need to make sure you check everything. Okay, and make sure you initialize everything. For example, the objective value, self-best objective value. So okay, never mind. Let me just show you. Well, and here, if OP type minimization, then we will set what? Self-best objective I equal what? Double initialize, right? Minimization, maximization. So hopefully, I mean, once we execute this line, because in the very beginning, the first solution should be better than the self-best solution. So within this function, we will populate the self-best position by that function. Else. So make sure, I'm not sure for that, but just use, and your coding, you should try, just use one pass can deal with all the initialization. That is the better, okay, and that's the logic should be better than multiple paths. So make sure you can put everything right here. But probably it is not the case. You need to set up maybe more than one path in order to make everything reset. I don't know. Depending on you make the decision yourself. So once we have reset, then we can display the position, right? We can display the particle. So how can we do that? So back to our form here. So in our form, we create a particle swarm optimizer, right? So right here. So button create PSO solver. So in addition to my problem object, we need to have particle swarm optimizer, my solver. All right, so once we have the problem, once we have my problem ready, right? So problem has been okay, and then we will instantiate an object of the particle swarm solver. So my solver equal what? Need particle swarm optimizer. So the constructor is defined by number of variable. How can you get a number of variable? Wow, I don't have this data, right? But remember that you have this object ready, my problem ready. So number of variable equal what? Oh, okay, I use my problem dot as its problem dimension. You see, the dimension is the number of variable dimension. How about lower bound? Oh, I do not have that. But again, since everything has a wrap up in this my problem, right? So my problem dot. Oh, again, another property, lower bound. Wow, fine, beautiful, right? Double there. So everything has been wrapped up by that class. So I kind of doing this kind of data structure design for you. So it's very simple. My problem dot upper bound, right? And automation type. My problem optimization goal. I call it optimization goal. Actually, is the optimization type, optimization goal. Okay, how about objective function? Definitely, you should provide your own function, right? But again, I know nothing about my problem. How can I provide a function? So never mind. Again, my problem dot. Excuse me. Let me. My problem dot. Okay, function, right? Function, right? Oh, okay. We have get objective value. So this is a function, right? In my problem object. So this is a object scope of function for my problem. So it's a function. The signature of this function, well, it's a double array, right? And return a double. So that will be consistent with the required dedicate. So I can just say that get objective value there. So as you can see, I do not have anything, right? I do not have data. I simply have my problem. So it turned out to be like that. Well, if that is the case, why your particle optimizer ask for so many parameters? Why not? Why just provide another constructor? Well, what he asks is a COP dot COP benchmark. The problem. Fine. Okay, so that is the way you conduct the so-called object-oriented design, right? But you need to assign this guy, right? So it's a simple, right? The number of variable. Okay, this number of variable equal what? The problem. Dimension. The same, right? So, okay. But in this case, you don't need to use this again because and probably I might call it arbitrary PP anyway. It represents that problem. So PP is the operation. Oh, okay. So kind of copy. So right now in your Python, provide two different. So PP dot lower bound, capitalize, right? PP dot upper bound. So lower bound, upper bound, 3D. Automation type, again, PP dot automation goal. And you instantiate the memory by yourself. Oh, okay, let me say, COP lower bounds, PP dot lower bounds, double array. Oh, okay, the typo is a typo. It's not plural. So lower bound, upper bound. Okay, fine. So in that case, in your method, well, either way, my solver is right there. So either way can do it. So the simplest way probably I just give my problem as the instantiate is the constructor. So similar. So it's simple, right? So it's much more simple. But roughly, well, actually for the particle solver, you need to know the number of variables. We need to know lower bound, upper bound, and automation type, and object function. So everything is already there. So once we create objects, my solver is ready, and then we can invoke my problem, right? No, not here. This instance is right after reset. So after reset, we invoke what? And you say we invoke my solver. My solver reset, right? So after reset, we might want to show the particle on the graph, right? So if in that case, we invoke my problem. You see, my problem display on panel. My problem display objective graph, right? So my problem display solution on graphics. Solution on graphics. So I need to provide the solution. Solution what? Solution has a number of particle, right? So it's a double type. So again, that is my solver solutions, excuse me, position. Right? So all the particle has been initialized by the PSO solver. So they have this kind of data there, position, right? So right now we publish that as a public property, so we can use that to show there. Okay, so that's the way we do it. So let us maybe set up a breakpoint to let you trace what happened there. Okay, extension there. Oh, okay, maybe, let me add another one. So once we create this solver, right, we knew it, then our PPG solver that selected object equal my solver. So we'll show the available parameters of the solver for the user. So open first. So you make sure you need to do the for proven. So problem continue. So if I choose the peak, okay, pop out everything's shown up right here. And it's about the time I create a PSO solver. So far, my solver is none, right? So we move this constructor. If I hit every given key, the initialization statement will be executed. 10 will be assigned to the number of particles. So 0.5, 0.5, new random. Okay, PB is ready, right? PB is ready. So you can check out about the PB property there. It's everything there. So number of particle currently is 10. Oh, I'm sorry, made a mistake. Number of variable. Sorry about that. So number of variable. PB dimension. Number of variable. Okay, sorry about that. So let me quickly open peek again. Create particle solver. So this time I simply pass it. Oh, let me still enter it. Step. Okay, number of variable. Initially is 0. So right now we know dimension is 2. Upper bound, lower bound, none, right? So right now we have -4, upper bound. This data has been prepared by the library, right? The library provides to you. Automation type and minimization. So far the best solution created. So right now solver version is ready. 0. Right? Okay, so solver is created, right? We show the property on public grid. So up to this point, everything seems okay. So up to this point, we set the position as property. We also have so far the best property defined it. So about the time we reset everything in order to run the evolution. So reset, when we quickly reset, we ask the solver reset to enter this function reset. Okay, this is reset. So position initially is none in the very beginning, in the very first time, right? So in the very first time, we need to allocate memory. So number of particle first. So I'm not going to cover everything. So again, you need to complete the rest of data structure initialization right here. So run to this point. So we randomly assign initial position. So let me execute up to this point. Oops, we have error, right? Okay, self-base is not allocate memory allocate yet. So, right. So, well, I simply comment it out so that you do that. Okay, so what I need is just the position. Okay, so you do the rest of the job. Open. Continue. Peak. Okay, it's about the time we end up. Okay, it's fine. It's almost done. So let's solve first. Reset. So enter reset right here. So okay, we are about to initialize the position. So currently memory has been allocated, but all value are 0, right? So after that, we can do this line. After that, position has been initialized with initial value. So random value has been initialized, right? So it's okay. So particle position has been set. Update so far the best. Sorry, I don't know whether it will crash or not. Okay, not implementation. Okay, so comment it out. Comment that out. You need to implement that by yourself. All right. So again, try it again. So disable that breakpoint. Peak. Particle zone optimizer created. Reset. So finish reset. And then we are about to display the solution on graphics, right? So position, take a look at that. Right now it has to be initialized. So random variable has been initialized. So let me go through it. So you will see the 10 particle has been initialized here. So that is the way you invoke. So one iteration you will update the current position in the similar way. So I'm going to do it. So if a user click another, click reset again. User did not change anything, right? So the second time, this is the second time. User did not change. Position has memory allocated, right? So and the position length is still 10. So particle number of particle is not changed by the user. So in this case, we are not going to reallocate memory at all, but instead we initialize the initial position with different random value, random value here. Okay. All right. So another hit or reset. Right now, I terminate the display. Okay. Reset. Again. Reset. So you will see the new solution actually is new positional particle on the figure in this way. All right, so the rest should be your job, okay, to complete the PSO evolution by yourself. Okay, if you really bump into any unsolvable problem, just let me know. Probably I forget to instruct you something. But I think almost everything has been done in this lab. Okay, so that will be all for today. So, well, finish your assignment as soon as possible because we still have should have a last assignment for the neural network lab. All right, so finish this assignment as soon as possible. Okay, now we'll go over today. Thank you.